Welcome back to the lectures in chemistry and the introduction to molecular spectroscopy series that I have been giving. Okay. So, in this lecture we will get to the practical aspects or the elementary aspects of rotational Raman spectra, and in the last two lectures I talked about polarizability and the fact that it is a tensor and it is connected to the, or it is the measure by which the induced dipole moment depends on the external electric field. So, now we will get to the actual spectroscopic details. So, we will start from the fact that mu induced is alpha times E. We will write it this way for the time being, that is as a scalar. And when we do the actual spectra intensity computation, we will use the fact that alpha is a tensor. Okay. Mu is proportional to alpha E. Now, please remember, for an external static electric field, alpha is a constant because the induced dipole moment depends on the electric field E. Okay. But alpha is not a static quantity because the molecule is not stationary. The molecule is actually vibrating. It is vibrating, say, with a frequency, angular frequency omega. Okay. Let us call it as a vibration frequency. So, if the molecule is vibrating, then alpha is actually also vibrating, is also changing in time by the simple relation alpha naught plus alpha 1 sine omega vibration times t. Okay. This is the polarizability as a function of time. Okay. This is due to the vibrations in the molecule. In the case of rotation, of course, in a rigid rotation we do not worry about it, we only worry about alpha 0. We do not need to know what alpha 1 is. But in general, molecule undergoes both rotation and vibration, and so far we have been, our considerations have been simple enough to treat this as two different phenomena, two independent phenomena. So, if you do that, then for the vibrational sake you will have both alpha naught and alpha 1 sine omega vibrational times t, but alpha naught will not be relevant for the vibrational spectroscopy. For vibrational spectroscopy, alpha 1 will be relevant because that is a changing polarizability. Exactly the same way the mu has to change during the vibration, the mu induced also has to change during the vibration. Therefore, the mu induced now will become, as a function of molecular vibration, it will become alpha naught plus alpha 1 sine omega vibration times t. But please remember, in the case of the electromagnetic radiation, the electric field of the electromagnetic radiation is not a constant, is not a constant in time. It is actually itself a sinusoidal function. Therefore, the electric field itself will be E naught in some direction, say let us call it as a z direction if you wish, okay, and it will be sine omega t. Plus phi if you want to put in as a phase factor, but we will consider a very simple thing, namely that the induced dipole moment changes during the vibration as a function of time due to two things. There are two oscillating components, an oscillating component due to the vibration and an oscillating component due to rotation. Now, this is the physical picture. Now, what is the Raman effect? Okay. We will start with this Raman effect. So, let us keep this in the background. When we need it, we will come back to this. What is the Raman effect? Light of some frequency nu naught irradiates a sample, and this is some sample. The scattered light which comes out This is a transparent sample. Therefore, what happens is a small portion of the light gets scattered, bulk of the light is transparent and it goes straight through. And the very small portion of the light that is scattered seems to have not only the nu 0, which is the frequency of the incident light, incident electromagnetic radiation, but the scattered light seems to have nu 0 plus delta nu 1, nu 0 plus delta nu 2. There is a whole series of frequencies of radiation which are emitted, as well as nu 0 minus delta nu 1, nu 0 minus delta nu 2. I mean, it is not the same delta, some value. So, if you want to, you write it as d nu 1. If you want to make it different, it is d nu 2, so on. Okay. So, there is also another group of frequencies which are seen in the light that gets scattered. That is, the scattered light has been modulated over the incident light frequencies by these additional frequencies or these depleted frequencies. It is somewhat easy to understand this from the quantum mechanical standpoint, why light that falls on the system comes back with different frequencies. You have already seen that, because if you think about this as a photon and the photon frequency matches with some transition between rotational energy levels or transition between vibrational energy levels, it is possible that the photon gets absorbed and the scattered light may have some amount of energy reduced from it to give radiation of this kind, or an excited molecule which actually comes down to a lower energy level introduces an additional different photon with a frequency which is different from nu 0, but slightly more than that. Okay. Now, there is also of course nu 0. A fairly large amount of light that is scattered does not have any intensity, does not have any change in the frequency. This nu 0 to nu 0, this is called Rayleigh scattering. Okay. These two together is called Raman scattering. This is the Raman scattering effect. Of course, the lines have very specific names. Light which has a frequency less than that of the incident frequency. This phenomenon of reduced frequency is called Stokes phenomenon, okay, or Stokes radiation. And radiation which has a frequency which is higher than the incident frequency due to the interaction of the radiation with the sample whose energy levels are quantized, and therefore there is a lot of energy exchange in them leading to changes in the frequency. This is called anti-Stokes phenomenon. So, let me write that here, anti-Stokes radiation. So, you get both, you get the Rayleigh scattering, you get the Stokes scattering, and you get the anti-Stokes scattering. Now, how do we understand this? We understand this from the last line that we wrote before we introduced to the Raman effect, namely the induced dipole moment that we wrote down is alpha naught plus alpha 1 sine omega vibrational t times E naught sine omega t. This is the radiation frequency. This omega is what we call, let us call this as omega naught because we are using the symbol nu naught. And the relation between omega naught and nu naught is, it is 2 pi nu naught. This is angular frequency and this is the regular frequency in the form of hertz. This is in terms of the angle. Okay. Now, please remember sin A sin B is 1/2 cos A minus B plus cos A plus B. Okay. Therefore, if you remember this relation, okay, what you see here from this one is alpha naught E naught sine omega naught t, that is the first term, and then you have alpha 1 E naught by 2 times cos omega vibration minus omega naught t minus cos omega vibration plus omega naught t. Okay. Therefore, you see that the induced dipole moment now has components, okay, components that correspond to dipole moment oscillating with the same frequency as the incident radiation, the dipole moment oscillating as the omega vibration minus omega naught, meaning that omega naught is no longer omega naught, but it is changed by, it is after all cosine. So, if you want to write this, you can say omega naught minus omega vibration, and this is also omega naught plus omega vibration. Therefore, the dipole moment thus has its own oscillations, and this results in the energy exchange, and therefore, the radiation that comes out also has frequencies corresponding to the original, the radiation of the original frequency nu naught, and radiation with frequency differences corresponding to some vibrational motion, internal vibrational motion of the molecule, internal vibrational motion of the molecule. This is a very elementary simplified picture to tell you why there is a modulation of the radiation that comes out. Okay. You see that frequencies are different, and there can be many because we considered only one vibrational motion, but molecules have more than 1 degree of freedom, and also the molecules, when they rotate, the induced dipole moment undergoes rotation, and the rotation induces its own frequencies, and rotation is connected to the alpha naught E naught, because for a pure rigid rotor we do not have alpha 1. There is no vibration, therefore, the polarizability is the static polarizability, but the static polarizability is a second rank tensor. It has XX component, XY, the YY component and the ZZ component in the principal directions, and therefore, there are 3 polarizability, static polarizability components which are part of the induced dipole moment. So, even if the molecule does not have a dipole moment, the presence of the electromagnetic radiation induces a dipole moment due to the fact that the molecule can actually polarize itself to the positive part of the electric and the negative part of the electric field, and continue to do that either through rotation or through vibration. So, since there is an induced dipole moment even in the absence of vibration, now there is a microwave spectrum that one can see, and that spectrum can be seen in the Raman lines in the next step. Okay. Okay. So, the rotational spectrum, when the molecule does not have a permanent dipole moment, it still has an induced dipole moment due to the electric field, and the induced dipole moment also is proportional to the alpha. So, if you recall, mu induced, now we will use the tensorial form that we had used. Suppose we had mu induced in the z direction, which is probably the direction of the symmetry axis of the molecule, then the mu induced is given by alpha z x E x plus alpha z y E y plus alpha z z E z. Therefore, this is the one which causes the molecular rotational energies to be accessible by Raman spectroscopy, because now they have polarizability which is also rotating because of the molecule is rotating, the polarizability tensor, the quantities also rotate. The mu induced is directly given by two directions, alpha zx or alpha zy or alpha zz. Earlier when we studied microwave spectroscopy, the Hamiltonian that we were worried about had basically the interaction with the external electric field is mu dot E. It is a scalar. The mu is the dipole moment vector and E is the electromagnetic radiation, and therefore what you have is this mu is due to the mu induced, and so the Hamiltonian due to this mu induced is this, and this Hamiltonian is responsible for the transition. This is the one which leads to the transition between rotational levels. So this mu induced is now a function of two coordinates or two directions. So it is like mu induced is like the molecular property of a coordinate z and a coordinate x. Earlier the mu in microwave spectroscopy was simply mu x of x plus mu y of y plus mu z of z. Okay. And these were the dipole moment components in some chosen direction, and x, y, z are the coordinate system that we start with, and therefore these are the mu x, mu y, mu z are the components of the arbitrary dipole moment in the direction of the coordinate system. Here the mu induced now depends on two coordinates, and therefore what this leads to is the selection rule of a delta j not plus or minus 1 but delta j 2. Also there is a invariant component alpha 0, and alpha 0 is usually defined as 1/3 of alpha xx plus alpha yy plus alpha zz, and I told you that this quantity does not change between different coordinate systems, and therefore this is called the scalar of the polarizability, and this alpha naught, which is a constant, okay, does not have any direction dependence, everything has been summed here. This constant therefore also gives rise to what is called a delta j is equal to 0 transition. In microwave spectroscopy you do not have a delta j is equal to 0 because there is no microwave spectroscopy then. Delta j is plus minus 1 for a rigid molecule. In the case of rotational Raman, the static polarizability, which does not have what is called a scalar component, which does not have any direction, leads to delta j is equal to 0, and the actual mu induced dipole, which involves two directions, leads to delta j is equal to plus minus 2. Therefore the selection rule for rotational Raman is 0 plus minus 2, and that is also for molecules which do not have a permanent dipole moment. Therefore now you have a beautiful handle of being able to detect the microwave spectrum of hydrogen molecule, the most elementary molecule that you have. Microwave spectra could not detect that. Raman lines, rotational Raman spectroscopy tells you how, if the hydrogen, the electrons between the two hydrogen atoms, if they are polarized due to the presence of the electromagnetic field, then there is a polarizability that comes into the picture, and this polarizability has one scalar component and several vectorial tensorial components, two in this case, the parallel and perpendicular polarizability, and this polarizability allows us to actually look at the rotational energy levels of hydrogen. So Raman spectroscopy is a beautifully complementary spectroscopy to study systems which are otherwise inaccessible to the spectroscopic techniques. So molecules which do not have permanent dipole moment are not seen in microwave. All those molecules which have any measurable polarizability, I mean unless the bonds are extremely rigid, and therefore the polarizability is extremely small. See, if you are very rigid, the field does not basically affect the electron density, but if the molecule is already undergoing some vibration and the 0 point vibration and the molecular bonds are slightly more flexible, then you see the polarizability leads to an immediate measurement of the microwave spectrum of molecules. Now what is the microwave spectrum of molecules? they have the following features. Okay. So if the selection rules are delta J is equal to 0 plus minus 2, remember we have what is called a nu naught. This is the Rayleigh line, the frequency that we have. So that's the center frequency. Okay. No modulation of the incident light that passes right through. Scattering equipment detects that right away. So there is no change in that. Okay. Now on either side we have delta J is equal to 0 or plus minus 2. Okay. So which side is which? Let's write down the energy levels. For a simple diatomic molecule, we have the energy levels E0, which is 0 because J is 0. The next one, E1, is Bj into J plus 1, it is 2b. J is equal to 1, it is 2b. Therefore, the gap is 2b. But then J is equal to 2, it is E2 is 6b. Okay. Same energy level spacings that we are familiar with microwave. But now between 0 and 6b you have a transition because delta J has to be 2. There is no transition between 0 and 1. There is no transition between 1 and 2. What about Ej? E3 is equal to 12b and this is J is equal to 3. There is a transition between 1 and 3. Okay. What's the difference between the two? This is delta E is 12b minus 2b, okay, 12b minus 2b, and that is 10b. Okay. What is the lowest frequency that we would measure? This delta E is the difference between 0 and 6b. Therefore, this is 6b. Okay. What's the next one? Let us draw, say, J is equal to 2 here, and that's a 6b. And the next, let us draw J is equal to 4. Okay. J is equal to 4. 4 is 4 into 5, so it is 20b. Okay. The gap between J is equal to 2 and 4 is now 14b. Okay. You calculate this, you will see every difference that you can measure in Raman spectroscopy for rotational lines, barring the first one, which is 6b, will always be 4b away from this, 10b, 14b, 18b, 22b, and so on. Therefore, what you will see in the rotational Raman line is on either side, this is absorption of radiation. Okay. Therefore, what happens if this radiation is absorbed? I mean, supposing this is the frequency reduction in the scattered radiation, then that is seen on this side of the frequency because this is Rayleigh and this is the increasing direction on the frequency. Therefore, this is Stokes side and this is the anti-Stokes side. Therefore, the first line that you will see is 6b. The next line that you will see is 10b from here, 0 to no transition. At this point J is 0. Therefore, J is equal to 0 to J is equal to 2. Then this is J is equal to 1 to 3. And then the next line is 14b, 18b, and so on. What about on this side? It's exactly the same. The other one is the emission of radiation because the transition happens from higher energy state to lower energy state. But remember, usually fewer molecules are there in the higher energy state and more molecules are there in the lower energy state. Therefore, getting transitions down from very high energy state to very low energies, because so few molecules are there, the intensity of that such radiation, that is the anti-Stokes radiation, is usually weaker than the intensity of the Stokes radiation, where nothing but absorption is happening. Therefore, the radiation that comes out does not have those frequencies. These are the nu naught minus 6b, nu naught minus 10b, nu naught minus 14b, and so on. Therefore, I would say, I would put something like 6b, 8b, this is 6b, this is 10b, this is 14b, due to this process, due to this process, due to this process. Okay. So, you see a very symmetric 18b spectrum on either side of it for a rigid rotor. The gap between the 0 and the first rotational line is 6b, and every other line is 4b. And what is B? You know from microwave spectroscopy that for a rigid diatomic molecule that we are looking at, the value of B is h by 8 pi squared IC, and therefore, if you have delta nu is equal to 6b, the first gap, the first appearance of a rotational Raman line. Hydrogen is a beautiful example, okay? And benzene, many other molecules, all molecules which are homonuclear. No microwave spectrum, everyone shows up in the Raman, in the gas phase. And what you see is the first line 6b is for j is equal to 0 to j is equal to 2, okay? And yeah, and the next line is every gap is 4b. Therefore, delta nu by 4 is the gap between successive lines, gap between successive Raman lines is 4b, okay, and that delta nu, and therefore delta nu by 4 is h by 8 pi square c mu r square. You know the reduced mass, therefore you can calculate the bond length very, very accurately for the molecule if you can measure rotational Raman lines. Okay. This is as simple as what one can expect. There are much more things in rotational Raman spectroscopy, particularly if the molecule is slightly non-rigid. Then there are centrifugal effects. We never studied centrifugal effects in this course, even in the pure microwave spectrum of molecules having permanent dipole moment. Therefore, I don't want to introduce that here. But remember, this is the starting point of understanding the selection rules. The selection rule being delta J is equal to plus minus 2, and the delta J is equal to 0 is right here. Okay. No change, okay. And so what you see is that this is how to interpret elementary Raman spectra, and looking at the spacing and then calculating the bond length, or the vice versa, if you know the bond length, exactly where the Raman line will be, and so on. Now, in the next small bit, I would talk about the vibrational Raman spectrum, and then we will come to an end with respect to this particular course on the molecular spectroscopy. There will be one introductory lecture in another 3 or 4 days. You will also see on electronic spectroscopy. The last segment of this introductory lectures on Raman spectroscopy. So we will look at vibrational Raman spectrum. Also only for the very elementary case of a simple harmonic model, or similar to that in the normal mode model for a polyatomic molecule. Now, remember vibrational spectroscopy, the intensity of the infrared transition is due to the rate of change of the dipole moment with respect to the displacement coordinate. So suppose x is the displacement coordinate. And during that displacement the dipole moment changes. It is the rate of change of the dipole moment with respect to displacement that is responsible, and this is how do we write that? We will write in a formal way. We will write mu at a position x is mu naught, which is basically mu at x is equal to 0, no displacements, or at equilibrium displacement, and then you have this is plus d mu by dx evaluated at the displacement being 0 times x plus and so on. Okay. It is this rate of change of dipole moment evaluated with respect to the equilibrium geometry that is responsible for the intensity of infrared spectrum. There are other terms like this rate of change, that is second degree, then there is a third degree and so on. That basically determines the extent to which the molecular motion is no longer harmonic and it is highly non-linear, and therefore higher order terms come in. But if we restrict ourselves to this term, this leads to the selection rule delta V is equal to plus minus 1. The static dipole moment is irrelevant as far as the infrared spectrum intensity is concerned, because that is a fixed component. There is no association with the position because it is a constant. But if the dipole moment keeps changing during the vibration, you immediately see that that vibrational mode is detected by the infrared spectrum. That is this coordinate, the rate of change, the rate of change as well as this coordinate. It is this which is the molecular level operator, I should say, okay, the position coordinate. It is that which connects the vibrational eigenfunction which contains one Hermite polynomial to another vibrational eigenfunction which contains another En prime, En double prime and En prime. If these two have to be connected, it is this mu, and technically it is the x operator which connects the psi n prime, the psi n double prime, to give you an intensity that of the transition between n double prime to n prime as being proportional to the absolute square of the integral psi n prime x psi n double prime of x dx square. Okay. Therefore, you see that because it is linear, it is x, not x square, not x to the 1/2 or anything else. Because it is linear, in the limit of what is called the harmonic approximation, where the rate of change of the dipole moment alone is sufficient for us to consider the motion. That is because the displacements are very small, harmonic motion. Therefore, the selection rule holds because this integral is non-zero only for n double prime is equal to n prime plus or minus 1. So this is the essence of the vibrational intensity. I might have talked about this in the lectures earlier. If I didn't, this is how we actually calculate the vibrational intensity. The intensity is proportional to the square of what is called the matrix element between the state psi n double prime, one of the energy states, and its next state psi n prime, and therefore this is also possible. This is absorption, this is emission. Therefore, delta V can be plus or minus 1. This picture does not change in the case of vibrational Raman spectrum. Why? Because of the following. For vibrational Raman spectroscopy, we are looking at mu induced. Now this mu induced is going to change also as a function of x. Please remember, the polarizability is now observed in the mu induced x itself, and the mu induced x is going to involve alpha times E, and this is the alpha is the E times that, and so what you have is d mu induced, sorry, let us write the other way around. Therefore, if we write mu induced x in terms of no, that is when when there is no vibrational amplitude, it will be mu induced 0 plus d mu by dx induced times x. Okay. So the molecular property that is responsible for vibrational motion is again this rate of change of the d mu index evaluated at x is equal to 0, which contains essentially the rate of change of alpha with respect to x, okay, because if you substitute that, you are going to get d alpha x or whatever, some quantity, either the x quantity or the y quantity, but let us take the scalar quantity, is d alpha by dx, again with respect to x is equal to 0 multiplied by dx. But please remember, this d alpha by dx at x is equal to 0 does not have anything to do with vibrational motion. It is a static dipole, the polarizability due to the external electromagnetic field, and therefore it is this component which is still responsible for Raman but vibrational. Exactly the same way that the dipole moment must change during the vibration, it is important that the polarizability changes during vibration, and in that case this leads to the same matrix element type that you have psi n prime of x, x psi n double prime of x, dx prime, dx, because this evaluated with no displacement is actually independent of this x, but it is needed, without which you will not see this term at all. If this is 0, this term will not be there. Therefore, vibrational Raman spectroscopy requires essentially the polarizability to change during the vibration, but the matrix element that connects the vibrational states, that matrix element is identical in terms of the eigenfunctions of the vibrational states to the single coordinate x. Therefore, the selection rule for vibrational Raman is also plus minus 1, no changes. Okay. But if you consider higher order terms, and if you consider anharmonic terms, and if you consider polarizability is a very large, if the molecule has a very large polarizability due to the weakness of the forces between the different atoms and so on, so that the external electric field can actually pull these molecules apart from each other, then it is possible that other terms, the higher order terms of polarizability may get involved and so on. But to the lowest level, the vibrational selection rule for Raman spectroscopy does not change by much. I mean, it does not change anything, it is still delta V is equal to plus minus 1, but there is a significant change in the rotational Raman spectroscopy, where the selection rule is delta J is plus minus 2 and 0. Okay. So these are usually mentioned in any of the elementary textbooks, but I will leave this lecture with one last note. I will make this as a statement, and a very nice and simple explanation of this statement is, of course, is already there in the one of the beautifully written elementary textbooks on molecular spectroscopy. I have also referred to that book as additional reference for you, the book by Banwell and McCash, Elaine McCash. Okay. The statement that I would say make for Raman spectroscopy is the following. Molecules which have a center of symmetry with center of symmetry, okay, those have IR spectra or Raman vibrational spectrum, but not both. Meaning that if there are many modes, for example carbon dioxide itself, elementary molecule, even hydrogen for that matter. Okay. Hydrogen has a polarizability that changes during the vibration. Hydrogen vibration does not lead to any change in the permanent dipole moment, which is always 0, but the induced dipole moment will be there for a molecule such as hydrogen. Therefore, hydrogen vibrational motion cannot be seen by infrared spectrum, but there is a very nice and beautiful explanation in Banwell and McCash on how polarizability changes during the vibration from positive to 0 to negative, and therefore that leads to Raman vibrational spectrum for that molecule. This is the same thing with all molecules which have center of symmetry such as carbon dioxide. Carbon dioxide has the center of symmetry at carbon, and its symmetric stretch does not have any dipole moment change, but during the symmetric stretch the polarizability changes. Therefore, the symmetric stretch is not detectable by IR, but it can be seen in Raman spectroscopy. Therefore, they are mutually exclusive. Molecules with center of symmetry have mutually exclusive IR spectra and Raman spectrum. Those vibrational degrees of freedom for which there is a dipole moment change during the vibration, they will be seen by IR spectrum, but they will not be seen by Raman spectroscopy. Those degrees of freedom for which there is no dipole moment change, such as the symmetric stretch in carbon dioxide and many other symmetric stretches in every molecule which has a center of symmetry, you will see them either some modes are IR detective, and those modes which are IR detective, IR active, some modes are IR active, and those modes which are IR active are not Raman active, and vice versa. But this is applicable only in the case of molecules with center of symmetry. Water, for example, has both rotational, vibrational, microwave and Raman rotational spectrum, because it does not follow any of these things. I mean, the dipole moment changes, there is an induced dipole moment, and therefore there is a polarizability change in every one of these vibrations. Therefore, all three modes of water molecule are both Raman active, and all three modes are also infrared active. The molecule also has a microwave spectrum, it has a rotational Raman spectrum. So, many more things can be said, and this was a great contribution by an Indian scientist in the early 20s and 30s to the evolving field of quantum mechanics and spectroscopy, and therefore in later lectures we will study more of this in another course with some details to the actual calculations of some of these matrix elements and the polarizability matrices and so on. This sort of formally completes the lecture on infrared and microwave spectroscopy that I intended to give for this course. I wish you all the best in the tests and the tutorials as well as the examinations, and hope that you will come back to the next course that will be offered again in this area sometime later by me. Thank you.